Dear students, welcome back to online version of our EMTL classes. Quickly we will see what we have seen in the previous class in the form of 5 quiz questions. First we will see what are those 5 questions. First one is, for a transmission line R equals to G equals to 0, then it is a dashed line. Second one, for a transmission line R by L equals to G by C, then it is a dashed line. Third one, the expression for input impedance for a lossy line is given by dash. Fourth one, the expression for input impedance for a lossless line is given by dash. And fifth one, the expression for reflection coefficient of a transmission line is given by dash. Now we will see the answers one by one. Yes, coming to the answers. First one is, for a transmission line R equals to G equals to 0, then it is, you know very well, R equals to G equals to 0, resistance and conductance is 0, then it is a lossless line. Answer is lossless line. Next, second one, for a transmission line R by L equals to G by C, then it is, what is distortionless line? Yes. Next, third one, the expression for input impedance for a lossy line is given by, for a lossy line, remember tan hyperbolic function comes into picture. So generally the expression for input impedance Zn equals to Z0 into something. So in that something there will be numerator and denominator. In the numerator both Z0 and ZL will be involved, and similarly in the denominator also Z0 and ZL both will be involved. Z0 is, remember, it is the characteristic impedance, it is not output impedance. Z0 is the characteristic impedance, right? So accordingly, for a lossy line, so what is Zn? So Zn equals to Z0 into ZL plus Z0 tan H gamma L divided by Z0 plus ZL into tan H gamma L, like this. So here observe, so Zn equals to Z0 into something. So something is having both numerator and denominator. In the numerator, so first already we are having Z0 into, so other term automatically comes into picture, that other term is ZL. So plus Z0 into tan H gamma L divided by Z0 plus ZL tan H gamma L. So in the denominator just interchange Z0 and ZL, and tan hyperbolic function will come as it is, right? So like that we have to remember. So for a lossy line, tan hyperbolic function will comes into picture, whereas for a lossless line, so in place of tan H gamma L, what you will get simply J tan beta L, right? So that we will see in the next slide. Yes, first one, yes, the expression for input impedance for a lossless line is given by Zn equals to same. So in previously for lossy line you are having tan hyperbolic function, now we are having in the place of tan hyperbolic function you will get simply J tan beta L. So what is the input impedance for this case? So it is Zn equals to Z0 into something. So into that something there will be numerator and denominator. So in the numerator ZL plus J Z0 tan beta L divided by Z0 plus ZL into J tan beta L, like this. Yes, Zn equals to Z0 into ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. Next, fifth one, the expression for reflection coefficient of a transmission line is given by, you know very well, direct. You have seen the same reflection coefficient in the case of unbounded media also. So it is here in transmission line, it is very simply gamma L equals to ZL minus Z0 by ZL plus Z0. Students, observe, denominator is having more value, ZL plus Z0, whereas the numerator is having least value or minimum value. So we are subtracting the characteristic impedance Z0 from ZL in the numerator, and we are adding the characteristic impedance Z0 to the load impedance ZL. So like that we have to remember. So here gamma L, L stands for line. Line means transmission line. Gamma. So we are having a lot of information about this gamma in unbounded media. So with that knowledge, so directly we have defined this gamma L in the previous class. Gamma L is ZL minus Z0 by ZL plus Z0. Now coming to today's class. Previously we have seen the types of transmission lines and what are the various primary parameters, secondary parameters, line equations, how to calculate various impedances like characteristic impedance, input impedance, and how to find out the maximum voltages, minimum voltages, maximum currents, minimum currents, V0 plus V0 minus, all these secondary parameters we have expressed in terms of primary parameters RL, GC, and again in the primary parameters, if R equals to G equals to 0, so that type of transmission line is called lossless line. If R by L equals to G by C, then that is called a distortionless line. And we have seen the clear differences between this lossy line, lossless line and distortionless line very clearly in the previous class. Now today we will see Smith chart. So what is Smith chart and how it can be used in transmission line problems, right? Any transmission line problem can be easily solved by using Smith chart. So before going to see Smith chart, we are going to see some more types of transmission line based on the properties of how the load impedance was placed. Students, remember, in any transmission line, so the original transmission line will be there. So at the starting end of the transmission line, we will connect a source called generator, and at the far end of the transmission line or at the destination point, we will connect an impedance called load impedance. So depending upon what type of load impedance you are connecting, so that means where you are taking the output from the transmission line. So based on that, there are different types of transmission lines. So first we will see those three different types of transmission lines, then we will go for Smith chart, right? Yes, what are the different load lines? So load means what we are connecting at the far end of the transmission line, right? So if you think carefully, the load can be of either short circuit and the load can be of open circuit, and the third possibility here in the case of transmission line is if the load impedance is exactly same as the characteristic impedance. Students, remember, the characteristic impedance Z0 for any transmission line is uniform throughout the length of the transmission line, whereas input impedance, output impedance and other parameters will vary. So that's why characteristic impedance plays major role in transmission line, whereas intrinsic impedance plays major role in unbounded media like lossless medium, lossy medium, free space conductors. Those already we have seen, right? So what are the different categories we are having? The types of load for the transmission lines, we will see first. They are, we now consider the special cases when the line connected to the load of impedance is ZL. Right. So first one is, if short circuited, you are not making any resistive part. So simply you have made a short circuit. So that is how much impedance we have provided? 0. If ZL equals to 0, that is the first case. And second one, open circuited. The output ends or output terminals of the transmission line are open. So what is impedance across a open circuit? Infinity. So here by taking the open circuit at the far end of the transmission line, so then the ZL equals to infinity. Then the third case, very important case, that is matched line. So matched line means we are making this ZL is exactly equals to Z0. Z0 is not output impedance, it is characteristic impedance, right? Now for these three cases, we will see one by one how will be the different parameters, like how will be the reflection coefficient, how will be the standing wave ratio. We will see one by one for this short circuited line, open circuited line and matched line. So first we will consider the very first one, that is short circuited line. The short circuited line we will get when ZL equals to 0, right? In this case, input impedance ZSC we want. So what is the original input impedance for any lossless line? We are having the formula. So what is this? We know that for a lossless line, Zn equals to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Students, observe here we are considering the lossless line, not a lossy line. So for lossless line, you will get a Z0 tan beta L. There will be no hyperbolic function, right? Now, so in this expression of input impedance Zn, So what we have to do, if the load is short circuited, that is having ZL equals to 0. So for that what we have to do is simply where you are having ZL, there you have to substitute 0. So by substituting 0 in this expression, so what you will get, ZL equals to 0. So in the numerator, so first you are having ZL, so ZL equals to 0. So the remaining term in the numerator is J Z0 tan beta L. Yes, coming to denominator, Z0 plus J ZL tan beta L. So ZL is 0. So you will get in the denominator only Z0. So this Z0 and multiplied with Z0 both cancels, and in the numerator you are having only one term, that is J Z0 tan beta L. So in this original expression of input impedance of a lossless line, simply substitute ZL equals to 0, then what you will get, the input impedance of a short circuited line represented as ZSC. So ZSC equals to only the second term in the numerator, that is J Z0 tan beta L, like this. So substituting ZL equals to 0, what you will get? The second term in the numerator. So J Z0 tan beta L. Right? So this is input impedance for a short circuited line. Similarly, second property we will see, reflection coefficient gamma L. So already we know the reflection coefficient gamma L for a lossless line is equals to ZL minus Z0 by ZL plus Z0. So here in this expression what we have to do is we have to substitute wherever you are having ZL, there we have to consider 0 value, as just how we have observed or we have obtained how you got the input impedance ZSC by replacing ZL equals to 0. Similarly, in the original expression of gamma L also, we will do the same thing. By doing so, what we will get is, so original expression is gamma L equals to ZL minus Z0 by ZL plus Z0. So here ZL is 0 in the both numerator and denominator. So minus Z0 by plus Z0. So what we will get is minus 1. So gamma L is minus 1 for short circuited line. Similarly, we will see one more important secondary parameter, that is a standing wave ratio. Yes. So already you know the relation between standing wave ratio and gamma L. So using that standing wave ratio directly you can obtain what is the standing wave ratio by taking ZL equals to 0. So that also we are doing in a systematic manner as we have done in the previous two cases, that is reflection coefficient and input impedance. Right. We know that for a lossless line, what is the original expression for S? S is 1 plus gamma L by 1 minus gamma L. Here substitute gamma L as minus 1 in the both numerator and denominator, then what you will get is S equals to infinity. So for a short circuited line, input impedance ZSC is J Z0 tan beta L, gamma L equals to minus 1, and standing wave ratio S equals to infinity. So please remember these three important secondary parameters. ZSC equals to J Z0 tan beta L, gamma L equals to minus 1, and S equals to infinity. Similarly, we will see other two cases also. What are the other two cases? If ZL equals to infinity, so that means if you open the output terminals, then how will be the same three: input impedance, reflection coefficient, and standing wave ratio. And one more, that is mature line. So what happens if you take ZL is exactly equal to Z0? Those two cases also we will see. Out of those two cases, first consider open circuit, that is ZL equals to infinity. So first one, what we will see? Input impedance. So the same procedure we are following. Input impedance ZOC, open circuit. Yes, the procedure is same. So first we have to consider get an expression for a lossless line. Then we have to substitute here ZL equals to infinity. Here directly if you substitute ZL equals to infinity in both the numerator and denominator, you will get indeterminate term, infinity by infinity. So don't substitute directly in this expression. So what we have to do is take ZL common. Take ZL common in both numerator and denominator. Then ZL gets cancelled, and the remaining terms, so Z0 by ZL, so denominator will become infinity, then that will be 0. So by doing so, what we will get is, So ZOC equals to minus J Z0 cot beta L. Previously for short circuited line we got ZS equals to J Z0 to tan beta L. Now it is exactly reverse with respect to sign as well as angle. Previously J Z0 cot beta L. Now it is minus J Z0 cot beta L. Here students remember, in the place of ZL you have to substitute infinity. Don't substitute in the direct formula of Zn. So first take ZL common, then ZL gets cancelled, then in the denominator term only you will get infinity, then make those terms 0, then you will get finally ZOC is minus J Z0 cot beta L. Now the second one, that is reflection coefficient gamma L. The same procedure, wherever you are having ZL, there substitute infinity. So we know that for a lossless line gamma L equals to ZL minus Z0 by ZL plus Z0. Yes, and this similarly. So don't substitute directly ZL as infinity, infinity minus Z0, we can approximate as infinity, and similarly ZL plus Z0, infinity plus some value, again infinity, infinity by infinity, it is indefinite term, we cannot define it. So first take ZL common. So if you take ZL common, ZL into 1 minus Z0 by ZL. So Z0 by ZL term you can make 0. Similarly in the denominator, taking ZL common, ZL into 1 plus Z0 by ZL. So both the numerator and denominator, the second term gets 0 and the common term ZL in both numerator and denominator gets cancelled. Then what you will get is gamma L equals to exactly 1. Gamma L equals to exactly 1. So previously it is minus 1, right? Similarly, the third property, what is that? Standing wave ratio. Yes, we will do the standing wave ratio in the similar fashion. A standing wave ratio S equals to, first we have to consider the original expression S equals to 1 plus gamma L by 1 minus gamma L. Here gamma L is 1. So substituting this, again we will get here S equals to again infinity. In the previous case also infinity, now it is also infinity. In the previous case gamma L is minus 1, now in this case gamma L is plus 1. In the previous case input impedance is JZ0 tan beta L, now in this case minus JZ0 cot beta L. Now don't be confused, to take the term which has to be infinity value as common term, right? Here, so if you are having some confusion with the intermediate terms, here in the expression of S equals to 1 plus gamma L, so you can consider modulus of gamma L also, if you are having some confusion with substituting minus L and plus L, right? And here what we have to remember is S is infinity for both open circuit as well as short circuit. Whereas other terms, gamma L is minus 1 for short circuit, gamma L is plus 1 for open circuit. Input impedance ZSC is JZ0 tan beta L for short circuit. For open circuit, ZOC is minus JZ0 cot beta L. Now we will see the interesting case, that is third case, matched line. Yes, what is the matched line? ZL equals to Z0. Yes. Similar procedure. Input impedance Zm. For short circuit we have considered as ZSC. For open circuit we have considered as ZOC. Now for matched line we are considering the input impedance as represented as Zm. Similar procedure is for a lossless line. What is the expression for input impedance? So Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. So here in the place of ZL substitute Z0. So what happens? So both numerator and denominator will become same. So both will cancel. So then what will get? Zn equals to exactly same as Z0. Right. Similarly, the second reflection coefficient we will see in the similar way. Gamma L original expression is ZL minus Z0 by ZL plus Z0. So here if you substitute ZL equals to Z0, so in the numerator Z0 minus Z0, 0. Denominator Z0 plus Z0, 2Z0. So what you will get? 0. So there will be no reflection coefficient. Gamma L 0 represents what? So what are the wave traveling from source to load? So at that load, by maintaining the load impedance as exactly equals to characteristic impedance Z0, there will be no reflections. It will travel through the load very freely without having any attenuations, right? Similarly, we will see the third property, that is standing wave ratio S. Standing wave ratio S Yes, what is the original formula? S equals to 1 plus gamma L by 1 minus gamma L. Here, substitute gamma L is 0. So 1 plus 0 by 1 minus 0. So what will get? S equals to 1. Right, for a mature line, if you see, the characteristics are very interesting. Zm equals to exactly equals to Z naught, gamma L is 0 and S equals to 1. Previously, for both open circuit and short circuited, standing wave ratio is infinity. So standing wave ratio infinity means, so whatever the wave you are traveling from source, so that wave is reaching the load, and at the load it is reflecting back in the form of standing wave. So that means in both open circuit and short circuited case, what happens is standing wave exists. If gamma is minus 1, you will have the amplitude reverse of the original forward wave. If you are having gamma as plus 1, so both are having the same positive values. Right? So that is the difference. So the same concept we have seen very detailed in unbounded case also. Remember, if gamma L is having either minus 1 or plus 1, definitely there will be a standing wave. If gamma L is 0, then the wave can travel into the other medium in that case. Now here it will travel through the load, right? So when it will travel through the load, so by making ZL equals to Z0. So if you make the output load impedance ZL is same as the characteristic impedance of the transmission line Z0, so then there will be no reflections. So actually for a wave, if you are having reflections, it is an advantage or disadvantage. So reflections should be avoided. So there should be no reflections. So in order to get no reflections, or in order to have the proper wave transmission through the load, so it is better to maintain the load impedance as same as the characteristic impedance Z0. Right. Now we will see, after seeing these three types of loads, what are those? Short circuited load, open circuited load and mature load. Now between these three we will see two important properties. Yeah. So first one, short circuited we know, open circuited. So short circuited is ZL equals to 0, open circuit is ZL equals to infinity, and mature line is ZL equals to Z0. Out of these three, which one is having a very good wave propagation? Third case, mature line, right? Yes. Now, so already we know the input impedance for the short circuited line as well as open circuit line. What is input impedance? ZSC, Z0 tan beta L. And what is the input impedance in the case of open circuit? So that is ZOC. ZOC equals to minus ZZ0 cot beta L. So if you multiply these two, what happens? So ZSC into ZOC I want. So what will happen? So ZSC is JZ0 tan beta L and ZOC is minus JZ0 cot beta L. So what you will get? Minus J square. J square is minus 1, minus into minus will get plus 1, and tan beta L multiplied with cot beta L. So what you will get? Both will cancel each other. So then what is remaining is Z0 into Z0. So Z0 square will come. So ZSC into ZOC is Z0 square, or you can write from this Z0 equals to square root of ZSC into ZOC. So it is a very important property. So the characteristic impedance we can express if you know the short circuited impedance and open circuited impedance. So from these two values you can calculate the Z0, or reverse also. If you don't know the characteristic impedance of the transmission line, but if you know the ZSC and ZOC, then you can calculate Z0 square as ZSC into ZOC. It is an interesting property between the transmission lines having various types of loads, short circuit, open circuit and mature line. And another important property, so that is for a mature line. So just now we have discussed out of these three, short circuit, open circuit and mature line. So which is the best line? That is mature line. So if you maintain the load impedance ZL equals to Z0 for any transmission line, then what is the advantage of getting? So no doubt there will be no reflections. Gamma L is 0, just now we have seen, and S equals to 1. So with this, so what may happen is, so by having the characteristic impedance at the load, then what happens is, so in addition to the no reflections, the maximum power can be transferred from source to load. So whatever the power you are having at the input, the same power can be transferred or propagated through the transmission line without any losses. So already you know the maximum power transfer theorem also in our circuit theory. So that theorem holds good here. So by maintaining the impedance of the load of a transmission line is same as the characteristic impedance Z0 of that transmission line. So practically the master line case will be mostly used due to this property. So what is this? So because of no reflections and due to this no reflections, what may happen? The maximum power will be transferred from source to load. Yes students, up to now we have seen three types of loads: short circuit line, open circuit line and mature line. Now we will see the interesting concept in transmission lines, that is Smith chart. Yes. So actually before the invention of these digital calculators and digital computers, engineers developed some sorts of tables, charts, graphs, etc. for the calculation and design and analysis of engineering problems, and one of them is a Smith chart. This Smith chart was developed by a scientist named Smith in the year 1939. Which year? 1939, right. So before the invention of these digital calculators, computers, so these charts plays major role. So now we are going to see how Smith has developed a chart and how the chart was useful to solve any transmission line problem, right. So if you want to use this Smith chart for the solving of any transmission line problem, so first we have to see what is this Smith chart, how it was constructed. So generally what is a chart or graph means, so what it should be the x-axis, what should be the y-axis on the graph, we will see. Similarly in this chart or graph, Smith chart or Smith graph, so what it consists of, we will see first, then we will see how it can be used to solve any transmission line problem. So first we will see the construction. As coming to construction, first one is the Smith chart is constructed within a circle of unit radius. The entire chart is having a radius of unit. Unit means 1. Yes, within 1 unit of radius, the entire chart will be prepared. The second point is the construction of the chart is based on the only one formula of the transmission line, that is gamma L, reflection coefficient of the transmission line. So that is ZL minus Z0 by ZL plus Z0. So before this slide we have seen in almost all the slides gamma L for short circuited, open circuited and mature line. You have seen this gamma L. Denominator is maximum value, numerator is minimum value. In the numerator we will subtract the characteristic impedance from load impedance. In the denominator we will add the characteristic impedance to the load impedance, right. And this gamma L we can write it as, so actually the problems in transmission lines will be very easy. So directly we have substituted the formula, but here this gamma L, input impedance and all the secondary parameters expressed in terms of primary parameters RL and GC, they are complex. They will have both real part as well as the imaginary part. So the conversion from this rectangular form to polar form or polar form to rectangular form will make the problem complex. So in order to avoid that complexity only, Smith has constructed and developed this chart called Smith chart, right. So whatever the formula you are having for gamma L, so that gamma L is expressed in terms of its magnitude, modulus of gamma L, and its angle theta of gamma L, or very simply we can express it as the real part and the imaginary part. Real part is gamma R, whereas imaginary part is J gamma I. So whatever may be the impedance, whether it is in the form of rectangular form or polar form. What is the rectangular form? This is rectangular form, gamma R plus J gamma I. And what is polar form? Yes, magnitude into angle. So that is polar form, right. Now So if you are using the Smith chart, so whether it is rectangular form or polar form, no problem. We can represent very easily and you can solve any complex problem by using Smith chart. How it will be very easy, it will be cleared after solving one or two problems in Smith chart. So before going to use the Smith chart for solving of transmission line problems, so first we are seeing the construction. What is the first point? So the entire Smith chart will be under one unit circle of radius. So it is circle, remember, right? So in circles, we are going to deal with the circles. And second one is, so whatever may be the characteristic impedance, whatever may be the reflection coefficient gamma L, so you have to express finally this as the real part and imaginary part. And next third point is, where gamma R is the real part and gamma is the gamma I or the imaginary part of the reflection coefficient as shown in the figure. We know it very well. Now we are going to draw the figure. So Smith chart is constructed within a unit circle. So here, so the entire radius is how much? 1 unit. 1 unit radius or 2 units diameter. Right. Within this, if you take the x-axis as real part gamma R, then what will be the y-axis? Its imaginary part, that is gamma I. Then if you see at this origin, so what are the values of gamma and S? If you know the value of gamma, immediately you can guess what is its corresponding S value, right? So at the origin, so the gamma value is 0. So correspondingly S is 1. Similarly, at the unit circle, at the outermost surface or outermost end of this unit circle, so gamma R will become 1, then S becomes infinity, right? Like this. Then I am taking the same unit circle into the next slide as well as, so with these 3 points the construction is not over. We are having a lot of steps, right? We will see the remaining steps under the construction. Yes, construction continues. Right. So the next point is, okay, we know the Smith chart is having only 1 unit of radius and at the center the reflection coefficient is 0, at the outermost edge the reflection coefficient is 1, and accordingly you can calculate its standing ratio. S is 1 at the origin and S is infinity at the outer surface. Now, if you are having one Smith chart, so that one Smith chart is enough to solve any number of transmission lines. So one transmission line may have one length and it is terminated with a short circuit, and another transmission line is having some another length and it may be short circuited, it may be open circuited with a ZOC, and another third type of transmission line may be there. So that transmission line may be having a load impedance exactly equals to Z0, which will have the maximum power transfer from source to destination. So like that, there may be different lengths of transmission lines. It may be lossless line or lossy line, distortion, whatever may be the type. So for all the transmission line problems, only one Smith chart is enough, but the condition is that the Smith chart, the impedance you are going to represent on the chart should be normalized. So here what do you mean by normalized means? So whatever may be the range of value of the load or input impedance or whatever it may be, and similarly whatever may be the length of the transmission line between the source and destination, whether it is lambda by 4 length or half wavelength of lambda by 2 or 10 lambda or 20 lambda, whatever may be the length, if you normalize the chart, then that single normalized chart is enough to solve any number of transmission line problems. Here the normalization should be, so generally normalization means what we will do, so we will divide the particular quantity with the maximum quantity, but having to Smith chart, so we will divide any impedance, whether it is input impedance or short circuited impedance or open circuit, whatever it may be, so we will divide it with its characteristic impedance Z0, not with the maximum impedance, we will divide with the characteristic impedance. Here, for example, the normalized load impedance small ZL, here this Z is small z, is given by small ZL equals to capital ZL by Z0. Capital ZL is without normalization. What is the load? So here, if you want to normalize the load impedance capital ZL, so we will just dividing with its characteristic impedance Z0. Then finally we have to express this in the form of R plus Jx. Previously gamma R plus J gamma I. Now it is R plus Jx in the normalized form. Here R represents what? Real part, and X represents imaginary part. For any load impedance there will be two circles. So one is the R circle, another one is the X circle. R circles are called the real part circles and X circles are called the imaginary part of circles, right? So under construction of the Smith chart, so what you have to remember up to now is, so a Smith chart will be having only one unit of radius. At the origin gamma R is 0, at the outermost gamma R is 1, and if you want to use a single chart for any transmission line of any length of any impedance, then it has to be normalized. So the normalized quantity will consist of two types of circles, real circles and imaginary circles. Now we will see what are these real circles and what are those imaginary circles, and how to draw, and after drawing those, how to represent a particular impedance on the particular Smith chart we will see. Yes. The circles corresponding to real part are complete circles. So if you want to represent the real part of the impedance, then you have to search for circles which are complete circles, right? Like this. So this is a unit circle. So under this there may be so many circles for different values of real values, like this, like this, like this, right? So all right hand side circles, all circles are coinciding at the right hand side point. Please remember, right? And so the outermost circle is having a radius of 1 unit, and the remaining circles will have the radius of smaller than this, and they are not having the radius similar to the first one. They are different. All these are having closed. All these are closed circles. So all these closed circles will represent a real part of the impedance. How it will be? What is the value of that real part? You will see very quickly. Right. Coming to second one. What is the second one? The circles corresponding to imaginary part are incomplete circles as shown in the figure. So there will be two circles, complete circles and incomplete circles. So complete circles represent a real part, incomplete circles represent a imaginary part. Right. Similarly, here also we have to consider the Smith chart under 1 unit radius. So under this 1 unit radius, the incomplete circles are like this, blue lines. So this is one incomplete circle. It is another incomplete circle, it is another incomplete circle, it is another incomplete circle, another incomplete circle, another. So like that the remaining part of the circles will be not comes under this unit radius of the Smith chart. They are also circles, but we are taking only some part of those circles. So that's why they are called incomplete circles. So all these incomplete circles are taken to represent the imaginary part of any impedance. Similarly, so if you combine these two, real part and imaginary part, then if you superimpose or combine this figure 1 for the real part, complete circles, and incomplete circles in figure 2, one onto another, then what is the combination you will get is nothing but a Smith chart like this. Combining both real and imaginary circles form the Smith chart as shown figure. Unit circle. Then first I am drawing here incomplete circles for imaginary part like this, then complete circles for real part. So this is the complete Smith chart. So here, in order to understand very clearly, or in order to avoid the complexity, we have taken the real circles of how many? 1, 2, 3, 4, 5, and imaginary 1, 2, 3, 4 at the top side, and 1, 2, 3, 4 at the bottom side. So why these lines are represented like this, you will see in the next slide. Right. For example, we want to locate a particular impedance value on the Smith chart, then it will be clear. So what are the real circles, what are the incomplete circles and imaginary circles, all those concepts will be cleared by taking one example. So that is the location of the image on Smith chart. As locating impedance. First, let us consider one example like this. So I want to represent an impedance Z equals to 2 plus J1 ohm. So how to represent this on Smith chart? So for this, the general procedure we want is, so whatever may be the impedance, so remember the impedance we are going to represent on the Smith chart should be normalized. So let us assume this is the normalized impedance. 2 plus J1 ohm is the normalized impedance. So in order to represent this normalized impedance, so what we have to do is, we have to separate its real part and imaginary part. So first, by considering the standard notation, what is the standard notation? Normalized form, Z equals to R plus Jx. So compare this Z equals to R plus Jx, the example 2 plus J1 ohm. Then what is R? R equals to 2. And what is X? X equals to 1. We get R equals to 2 and X equals to 1. Now, if you want to locate this impedance value, Z equals to 2 plus J1 ohm, so it is nothing but the intersection of two circles. One is R equals to 2 circle, another one is X equals to 1 circle. R equals to 2 circle is a complete circle. X equals to 1 circle is not complete, it is incomplete circle. So in order to represent the impedance Z equals to 2 plus J1 ohm, what we have to do is, we have to identify the intersection point of the real circle R equals to 2 and imaginary circle of X equals to 1 on Smith chart. Right now, you know what is Smith chart? You have to consider a unit circle. Under the unit circle, there may be some other sub-circles, complete circles for different values of real part, and other circles called incomplete circles. Just now you have seen. Now I am drawing all those circles once again for our reference. Right. So I have considered the total constructed Smith chart at a time. Now here. So what is this outermost circle represents? What is its real value? So the outermost circle real value is R equals to 0. Then another circle after this will have some value of R equals to 0.5, and another third circle will have some R equals to 1, and another fourth circle R equals to 2. Here for the convenience I have taken only 4 circles, and again fifth one is also there 5 circles, but in original Smith chart there may be a lot of circles. So for any part of the chart you will have definitely some real part circle will pass through that point, and definitely some imaginary circle will also pass through that point. But in order to avoid the complexity, in order to understand clearly, here I have considered only 5 circles. So let us assume. So how to know these R values? So why you have considered, sir, R equals to 0 only for the outermost, and what about in between R equals to 0 and R equals to 0.5? There may be another circle. Yes, there may be another circle. So all those values how to read? So they will be indicated on the chart itself. You no need to worry about the values of where is R equals to 0 and where is R equals to 5 or where is R equals to 20. And finally, if you go to this top rightmost coincidence point, so where what will be R value? Infinity. So left side R equals to 0, right side R equals to infinity. So let us assume, so this red colored circle is, for example, R equals to 2. Then so we want the imaginary part also in order to represent the image. So only by considering a real part, the representation of impedance point will be not complete. Now coming to imaginary part. So blue line, the first horizontal blue line will have x value of 0, and the next line will have x equals to 0.5, and another line below this x equals to 0 line will have exactly the reverse value of this x equals to 0.5, that is a negative value, that is x equals to minus 0.5, like this. And then similarly the next line will have x equals to 1, and at the bottom side we will have x equals to minus 1, and then the intersection of these x equals to 1. So students, remember here, for positive imaginary parts we have to consider the incomplete circles at the top side portion of the Smith chart. All the bottom side incomplete circles on the Smith chart will represent a negative real part, negative imaginary part, right? And above the, that means top portion of the Smith chart, incomplete circle will represent the positive imaginary part. Top side positive imaginary part, bottom side a negative imaginary part. Here also, so between x equals to 0 and x equals to minus 0.5, you can draw another line exactly at the middle, so that may having x equals to minus 0.25. Similarly, at the top side, so between x equals to 0 and x equals to 0.5, you can draw one more incomplete circle, so that incomplete circle is may have x equals to 0.25. So like that, if you consider any point on the Smith chart, so that point may have definitely some real part and some imaginary part. So top side will represent a positive imaginary part, bottom side will represent a negative imaginary part. Now if you want z equals to 2 plus j1 ohm, so you have to highlight the circle r equals to 2 and another imaginary circle, that is incomplete circle, x equals to 1. So where these two are intersecting, so at this dot, so this dot will represent, so that point will represent an impedance of how much? Z equals to 2 plus 1 ohm. So like that, any impedance, normalized impedance value we can represent in Smith chart. So we will complete the location of impedance point on the Smith chart by considering another example also. As another example we are considering is z equals to 1 minus j 0.5 ohms. Right. As usually, so what is the first step? You have to compare with the standard normalized form z equals to r plus jx. By comparing with this r plus jx, we get r equals to 1 and x equals to minus 0.5. Now, in order to represent the impedance 1 minus j 0.5 ohms, so we want to get the intersection of the two circles, that is r equals to 1 circle and x equals to minus 0.5 circle. X equals to 1 circle is a complete circle, x equals to minus 0.5 is the incomplete circle. Here x equals to minus 0.5 means real part is negative, means we have to see the bottom portion of the Smith chart. Right. So now again I am considering the Smith chart as it is, right, by representing the real circles r equals to 0, r equals to 0.5, r equals to 1, r equals to 2, and then next x equals to 0, and here I am not taking the r value after this r equals to 2. It may have r equals to 20 or 50 or up to, if you go to the top finest point, it may be r equals to infinity. But for this problem, I want only at r equals to 1. So that's why I have stopped it. Similarly, imaginary part, this is x equals to 0 and above this x equals to 0.5 and below this, what is that? X equals to minus 0.5. So that's what we want. So that's why I have considered that line in the red color. Similarly, r equals to 0 circle in the red color. So where is the intersection of these two? So let us represent the remaining values also. Right, then the intersection of these two circles. One complete red colored r equals to 1 circle, another incomplete x equals to minus 0.5 circle. They are intersecting at this dot, black dot. So at this dot, so how much is the impedance? Z equals to 1 minus j 0.5 ohms. So like that, we can represent any value of impedance on Smith chart. Students, remember here, in order to understand clearly, we have considered only 1, 2, 3, 4, 5 real circles and 1, 2, 3, 4 imaginary incomplete circles above the top and 1, 2, 3, 4 at the bottom side imaginary circles for the negative values, right? So but actually if you consider the Smith chart, so they will have lot of complete circles and lot of imaginary circles. So the total unit circle is with full of lines. So we will see in the next class what is the full Smith chart and how to represent the impedance. So already I have seen two examples of the impedance. So for any intermediate value, for example, x equal here the real part we consider for easy understanding 1. So there may be impedance of 1.0008 ohms. So that value also can also be represented on the Smith chart. So for that also there will be a real circle passing through at that value. Similarly, here we have considered the real part as minus 0.5 and there may be practically some value minus 0.21235. 0.21235. So for that also there will be a circle definitely passing through on the Smith chart, right? So please make a note of it. Then coming to today's summary. First one is expression for the input impedance of a short circuited line is dash. Second one, expression for the input impedance of open circuited line is dash. Third one, expression for the input impedance of a matched circuit line is dash. Next, fourth one, closed circuits in Smith chart represents dash part of the normalized impedance. And last one, open circuits in Smith chart represent dash part of the normalized impedance. We will see the answers one by one. First one, expression for the input impedance of a short circuited line is short circuited line ZSC equals to Z0 tan beta L. That's all. And expression for input impedance for open circuited line minus J0 cot beta L. So first one is J tan beta L and second one is minus J cot beta L. Right, next third one, expression for input impedance of a matched circuited line. So Zm equals to Z0 is answer. Next fourth one, closed circles in Smith chart represents what part? Completed circles. Closed circle means complete circles represents what? A real part. So real is the answer for this. Yes, last one, open circles in Smith chart represents. So open circle means incomplete circles. Incomplete circle represents what? Imaginary part, right? So first one is J Z0 tan beta L. Second one is minus J Z0 cot beta L. Third one is Z0. Fourth one is real part. And fifth one is imaginary part. Right? Now, we will see the remaining two parts, that is a different length transmission lines and microstrip line. So here different length transmission lines means, so we have seen various types of transmission lines like parallel wires, waveguides, coaxial line, a plane on a conductor, like that. Not those types we are going to see. And we have seen depending upon the loads also there will be short circuited line, open circuited line, matched line. Not again those types. Different length transmission lines. For example, if the length of the transmission line is lambda by 2 half wavelength, then how will be the various characteristics? How will be the characteristic impedance Z0, input impedance Zin, reflection coefficient gamma L, standing wave ratio S. So all these parameters, how they will depend upon the length. So those different types of length transmission lines we will consider, and again we will see microstrip lines and with some other Smith chart problem. So in the next class we are going to consider the practical Smith chart. Onto the practical Smith chart, how to solve the transmission line problem we will see. In the next class we are doing the transmission line problem using Smith chart. Okay students, I hope you have enjoyed the today's class. Okay, see you. Bye bye and see you in the next class.